welcome to gemchem. Now today's video is on periodic properties part 5 video, where we will learn about ionization energy or ionization enthalpy. Now before starting, if you have not watched the previous parts of periodic properties video, please do watch it. I will give the link in the description box as well as the I button present above this video. So let us start today's video. Now see, what do we mean by ionization enthalpy? The ionization enthalpy has a theoretical definition which we are going to learn. It is actually the enthalpy change when 1 mole of gaseous species is transformed to the corresponding cation at 0 Kelvin. Suppose this is a gaseous species, so it will lose electron to give this ionic species plus the electrons. So this process is being monitored and the enthalpy change involved in it is the ionization enthalpy. Now let us see next part. This is normal definition. The minimum energy required to remove the most loosely bounded electron completely from the outermost shell of a free isolated gaseous atom of the element in its ground state, that is the lowest possible electronic energy state, provided both electron and the gaseous ion has zero kinetic energy and a zero thermal energy. That is, there are energy levels. The most loosely bound electron present in the last valence shell is being lost, and the enthalpy change or the energy change involved is known as the ionization enthalpy. Usually it is measured in electron volt or kilocalorie per mole. Now see this one. When it loses one electron, we have I1. When it loses second electron, we get I2. And when it loses third electron, we get I3. And generally, this is the pattern. That is, energy required for the losing of first electron is much lesser than the second, which is much lesser than the third. Why is it so? As an electron is removed from an atom to form a monopositive ion, the unchanged nuclear charge holds the remaining electrons much more tightly. So one requires greater energy to remove the second or the consecutive electron from the monopositive ion. Hence the second IP or ionization potential or ionization enthalpy of an electron is always greater than the first one, and when we generalize it, we get this one. Now the zeroth ionization enthalpy. What is that? The zeroth ionization enthalpy and the first electron affinity, that is affinity to grab an electron I0, is just reverse process. Right. Now what are the factors which control the ionization enthalpy is important to know. Now first factor comes as size of atom, that is size of atom. Now size of atom, as size of atom increases, outermost electrons lie farther away from the nucleus, so away from the nuclear charge, and hence IP value decreases. Easily it is removed. Now the next case is charge of the nucleus. Now see, if other factors remain same, then it depends. This IP value depends on generally this factor, that is charge of nucleus. As the charge of nucleus increases, the IE value also increases, that is ionization enthalpy value also increases. Now ionization value also increases. Now see this part, interpenetration and consequent screening ability of orbitals. Now see this part. Interpenetration concept has already been explained in the radial distribution curve and the radial distribution function video of atomic structure, and the screening effect is also being explained in the periodic properties video. I will give the link in the description box as well as the I button present above. Please do watch it, it will be helpful. Now see, the penetration capability and the screening efficiency of the orbital is S, then P, then T, and then F, right? We know that from our previous knowledge. So more effective the screening, easier it will be to remove the outermost electron, that is lower will be the IP value. Now the next point is overall charge of the ionic species, that is withdrawal of electron from positively charged species is more difficult than from a neutral atom, we know. Thus on increasing this one, overall charge of the species, ionizing the species, we can see that there is large influence on IP value. The IP value goes up. Ionization enthalpy is high in value. Now the last point is the type of electron which is involved. That is this point. Now the type of electron involved, the net force acting on the most loosely bound electron is determined by the nature. A typical case is provided for oxygen and sulfur. Generally a half-filled or full-filled shell corresponds to a stable configuration and hence shows high IP value. Now we go for the next part. We see the trends in first ionization value for S and P block elements along a period. Now see, first thing is this part. We see that we knew that as atomic number increases, it would have increased like this, right? That is for the graph. We should have got this plot. But actually we are getting something like zigzag. Not exactly the requirement fulfilled. So we see from lithium to barium it is increasing, but from barium to boron it is decreasing. So we need to explain this part. This can be explained actually by using radial distribution curve. Now see what is the radial distribution curve. Now see this part. This is the radial distribution curve, right? Now what is the process of ionization? In ground state it is He 2s2, right? And when it loses one electron and produces I1, so it is B plus in ground gaseous state, right? So this is the first excited state where it loses one electron and the configuration is here helium 2s1, right? Similarly for boron, it is helium 2s2 2p1, right? And when it loses one electron I1, then it becomes helium 2s2, right? So both cases there is s orbital at the last. Now see, here in this case, for this only we are seeing. Next we will see for this one. This is the radial distribution curve. From this it is evident that orbital penetrability of 2s is greater than 2p. So the nuclear attraction for the 2s electron will be greater than that in 2p. So it is for this reason that the removal of electron from 2s requires greater energy. So thus barium I1 value will be higher since it involves removal of electron from 2s, and for boron I1 value will be lower since electron has to be removed from 2p, right? This is from 2s and this is from 2p. So that is why there is a anomaly in the diagram. Now we will see for the next one, that is this part. Here see nitrogen and oxygen is our concern. So what is the configuration of nitrogen? We know nitrogen is helium 2s2 2p3, and when it gives up one electron I1, we get N plus in gaseous state, and the configuration is helium 2s2 2p2, right? And for oxygen, what is it for oxygen? Oxygen we have already seen helium 2s2 2p4, and I1 is O plus in gaseous state helium 2s2 2p3. Now just we see that for this is decreasing, that is the energy required to remove the electron from oxygen is decreasing. Now see, there is a presence of half-filled configuration here. For p orbital, we know for p orbital actually there is 6 positions to be occupied. So this is the half-filled model. So this is a stable configuration. We know for this E exchange is actually, what is the value of E exchange? 3 minus 1 by 2k equal to 3k. Now calculation of exchange energy is already being told in atomic structure part 10 video. If you have not watched it, please do watch it. I will give the link in the description box. Now let us see this one. for this configuration we are now calculating, it is equal to 2 minus 1 K by 2, and the value is only K. Now for this one we see E exchange equal to 3 minus 1 K by 2 plus 1 minus 1 K by 2, and this is equal to 3K. And for this one E exchange is also equal to 3K. So we observe that for first case, that is this one, for nitrogen, there is a change in exchange energy, and the change is equal to 2K, right? From 3K it is becoming K, and for this the exchange energy is equal to 0K. So from the electronic configuration of nitrogen, it is evident that during first ionization, half-filled P3 configuration is lost. That is, the process is not favored. Also, since the magnitude of exchange energy decreases, the process will require greater amount of energy, that is I1 of nitrogen will be high. Now in case of oxygen, we see that the half-filled P3 configuration is gained upon ionization. The process is highly favored, and this is also evident from the change in the exchange energy value, which is 0. Thus the process requires lesser amount of energy, that is I1 of oxygen is low. Now we will go for 3D elements. See for trends in I2 value for D block elements along a period. Now for this we see anomaly here and here, right? So we need to explain for chromium and manganese as well as copper and zinc. So we will first explain for chromium and manganese. Now for chromium, the configuration is actually argon 3d5 4s1, and this on losing 2 electrons giving out I2 value gets converted to chromium 2 plus, and the configuration is argon 3d4. Similarly for manganese, it is argon 3d5 4s2, and it on losing 2 electrons becomes manganese 2 plus, and the configuration is argon 3d5. Now the exchange energy is for this 10K. On calculating we get 10K. For this configuration it is 6K. For this one it is 10K, and for this one it is actually also 10K. So we see that half-filled D5 configuration for this case is being lost, and the magnitude of exchange energy is also decreased by 4K. This is 10K and this is 6K. Whereas for manganese there is no change in exchange energy. Net exchange energy change is 0, and half-filled D5 configuration of manganese is written. Thus there is a decrease in ionization energy. Now we will see for copper and zinc. Now for copper, the configuration is argon 3d10 4s1. Now it loses 1 electron to give argon 3d10. Then again loses 1 electron, this is I1 and this is I2, to give us argon 3d9. Similarly zinc, for zinc we see that it has configuration of argon 3d10 4s2, right? This on losing 1 electron becomes argon 3d10 4s1. Again on losing 1 electron it becomes argon 3d10. Now by doing this configuration only we can understand that there is a stable configuration, that is this is 3d10, so it is highly stable, whereas here the 3d10 is being lost, so there is a problem. So we calculate the exchange energy also. Now for this, the exchange energy comes to be as near about 20K, and for this it is 16K. And again for this it is 20K, whereas for this it is also 20K. So there is no net change in exchange energy for zinc case, and here there is a change in exchange energy which is about 4K. So we see full filled D10 configuration is lost for copper, and net change in E exchange is 4K, and full filled D10 configuration retained for zinc, and the no net change in E exchange energy. So this is the explanation for the anomaly present here. Now we see for trends in I3 for lanthanides. Now lanthanides, we know, we have already seen lanthanide contraction in periodic properties video, part 4 video, right? So here see, from cerium to europium it is same, but for europium to gadolinium there is a decrease, whereas for ytterbium to lutetium there is a decrease. So why this occurs? Now we first write the electronic configuration of lanthanides, which is xenon 4F14 5D 021 6S2. This is the electronic configuration, and from electronic configuration we can see that lanthanides, there are 3 outer electrons, that is here and here, right? So 2 in 6s and 1 in 3d, 2 in 6s and 1 in 5d, right? So thus these 3 electrons may be readily lost, but the electrons from the inner deeply seated 4f orbitals cannot be lost. Hence lanthanides will exhibit trivalency, right? Now see, this is a trend, and the 2 parts we need to mention here is this. Now we will deal with first europium and gadolinium. Now for europium. For europium the configuration is xenon 4F7 5D0 and 6S2. Okay, now this, on becoming europium 2 plus, has a configuration of xenon 4F7 5D0, and on losing another electron it becomes europium 3 plus, and the configuration is xenon 4F6. When we calculate the exchange energy right in front, we get E exchange for this one as 21K, and for this one we get E exchange to be as 15K. And when we do it for gadolinium, we know the configuration of gadolinium to be as xenon 4F7 5D1 6S2. When it becomes gadolinium 2 plus, here the configuration is 4F7 5D1, and gadolinium 3 plus becomes as xenon 4F7. Now from here only we can see that this is the stable electronic configuration as it is half filled, right? So we also see the exchange energy. Now the exchange energy for this one is near about 21K, and for this also it is 21K. So there is no net change in E exchange energy, right? So it is equal to 0. And for this one there is a change from 21 to 15. So there is a change of 6K. So this is the reason why the anomaly occurs. Similarly for ytterbium and lutetium, if we write the configuration only, we can understand. Now for ytterbium it is For YB, that is ytterbium, it is xenon 4F14 5D0 6S2, and ytterbium 3, first we will write for 2 plus, it is xenon 4F14, and ytterbium 3 plus is xenon 4F13. So there is a loss of electron from a stable electronic configuration, that is F14. And for lutetium, it is actually xenon 4F14 5D1 6S2, and lutetium 2 plus, it is xenon 4F14 5D1, and when another electron is being lost, then it becomes xenon 4F14, that is, it is gaining the fully filled F14 configuration, so the IP value will be less, and the E exchange energy for this one is 42K, for the next one is 36K. So there is a net change in 6K values, but for this configuration, for both cases 42K, and for this it is also 42K. So there is no net change in the exchange energy value. So this is the reason for the anomaly to occur here. Right. Now we will go for the next part, that is trend in I2 value for S and P block elements along the third period. Right. Now see this one. Here there is a decrease from sodium to magnesium. This is a anomaly here. Next here, that is aluminium to silicon, and the last one is from sulfur to chlorine. Now first thing, here there is a preference of going increasing, right, but it is not increasing. Similarly here also there was a requirement to increase, or it can decrease, but there is somewhere midway in between. So we will explain each and every part. Now for sodium, let's start with sodium. Now sodium has electronic configuration of neon 3s1. Then on losing 2 electrons, it becomes helium 2s2 2p5, right? And magnesium similarly has a configuration of neon 3s2, and on losing 2 electrons, it becomes Mg2 plus and has a configuration of neon, which is the stablest one. So there is a decrease here observed, right? Now we need to explain this. Now what is the explanation for sodium? The second ionization involves actually the disruption of the noble gas configuration. Process is less favored, requiring greater amount of energy. For magnesium, the second ionization leads to the formation of the noble gas configuration, and the process is highly favored, requiring lesser amount of energy. Thus this trend occurs. Now we will see for aluminium and silicon. Now first we write the configuration, right? For aluminium, the configuration is actually neon 3s2 3p1, which on losing 2 electrons, first it loses electron to give neon 3s2, that is loses electron from 3p. Similarly for I2, the configuration becomes neon 3s1. Now for silicon, the configuration is neon 3s2 3p2. So I1, it loses electron from 3p, so it is 3s2 3p1. Now it loses electron from p. Previously it was from s and now it is from p. So the I2 is neon 3s2, and this is a stable configuration, right? So we can also see the radial distribution curve here for 3p and 3s. During the second ionization of aluminium, electron is lost from 3s, while for silicon it is lost from 3p. Since the orbital electronegativity of 3s is greater than the 3p, radial distribution is shown beside. Now the nuclear attraction for 3s electron will be greater than that of the 3p. Thus removal of electron from the 3s of aluminium plus will be less favored than the removal from 3p of silicon plus. Thus I2 of aluminium is greater than silicon. Now we will see for sulfur and chlorine. Now what is the configuration of sulfur we need to write? This is being explained using exchange energy. Now neon 3s2 3p4, right, and S plus is neon 3s2 3p3 and S2 plus is neon 3s2 3p2. Removal from a stable electronic configuration where p3 is being present. Similarly for chlorine we see neon 3s2 3p5, which on losing one electron becomes Cl plus, right, and the configuration is neon 3s2 3p4, which on losing electron becomes neon 3s2 3p3, that is, it is gaining a stable electronic configuration, and we can explain it also on the basis of exchange energy. For this the exchange energy is 3k. For this the exchange energy is actually k. For this part, that is for chlorine plus, the exchange energy is 3k, and for this one also the exchange energy is 3k. No net change in exchange energy for Cl(I2) for the second ionization, whereas for this one there is a net change of 2k, that is, there is a net change of 2k. So this is the reason we know from the electronic configuration of sulfur. It is evident that during second ionization of sulfur the half filled p3 configuration is lost and the magnitude of exchange energy also decreases. For chlorine the half filled p3 configuration is gained upon second ionization and the change in exchange energy for the process is 0. Thus it is expected that I2 of chlorine should be lesser than that of the sulfur. But as we move from sulfur to chlorine, the effective nuclear charge also increases, and this should be also taken into account for the higher I2 of chlorine than the expected. It would have decreased a lot, but since there is an increase of nuclear charge, there is a slight, it is present slightly above, right? So as a result of this, we see that there is a slight increase as well as decrease, not direct decrease, right? Now we will see for the next part. Now we see the trend in I1 for p block element down the group. Now see this one, here is the requirement. Down the group IP value must decrease, right? So here decreasing, but here there is an increase from aluminium to gallium and silicon to germanium, right? So here basically from the electronic configuration we have already seen for aluminium electronic configuration, and for gallium we need to see the, let us write the electronic configuration first. That is for boron it is helium 2s2 2p1. For aluminium it is actually neon 3s2 3p1, gallium argon 3d10 4s2 4p1. For indium it is krypton 4d10 5s2 5p1, and for thallium it is xenon 4f14. Here f orbital contraction we can see f 6s2 6p1. So from the electronic configuration it is evident that the principal quantum number increases from aluminium to gallium, right? And this should account for the decrease in ionization energy, but in gallium there is d contraction, that is presence of d orbital here. Poor screening efficiency of 10 d electrons, and this should lead to increase in ionization energy, right? These two above effects are almost equally predominant, and these causes the anomaly present here. Now see, note from gallium to indium. Here, so there is a difference in configuration as increase in principal quantum number, and hence the nuclear attraction from the outermost electron results in ion, that is indium, will be lesser than that of the gallium. We are done with aluminum and gallium. We will now deal with for this part, that is silicon and germanium. So first we write actually the configurations which we need to know and we need to summarize. Helium 2s2 2p2, right? For silicon it is neon. For silicon it is neon 3s2 3p2. For germanium it is argon 3d10 4s2 4p2. Whereas for tin it is krypton 4d10 5s2 5p2. And for lead it is xenon 4f14 5d10 6s2 6p2. Now see here, at this case here the effect of actually the principal quantum number slightly predominates over the d orbital contraction, that is the d orbital present here. Whereas for this case, that is present here for indium to thallium as well as for tin to palladium, if contraction slightly predominates over the effect of principal quantum number. So here we can write or summarize here that PQN predominates over d orbital contraction, whereas for the second case where we see here F contraction predominates over principal quantum number. So this is important. Now we will see for the trends in I1 for d block element down the group. Now see here we need to write the configuration first. So 3d nickel argon 3d8 4s2, whereas for 4d it is palladium krypton 4d10 5s0, whereas for 5d it is platinum and it is xenon 4f14 and 5d 9 6s1. So we here see that there is a change right here. For nickel, electron has to be removed from the 4s orbital, while for palladium electron has to be removed from fully filled d orbital. Since the d10 configuration is extremely stable, that is 20K, so palladium requires greater amount of energy as compared to that in nickel. Thus, I1 value of palladium is greater than nickel. In case of platinum, the electron has to be removed from the relativistically contracted 6s orbital. This will require much more energy, greater amount of energy, and hence I1 of the platinum is much larger than that of the palladium. Now we see for this one, that is group 11 and 12. If we write the electronic configuration for copper and zinc, Au, and similarly for cadmium, mercury. Now Ar 3d10 4s2, krypton 4d10 5s2, and for Mercury, it is xenon, 4f14, 5d10, 6s2. Right. Now from electronic configuration of zinc, cadmium and mercury, these electronic configurations are near about similar, except in this case that is 4f14, and here d electrons are same for these. So the deciding factor is the principal quantum number. From zinc to cadmium, the principal quantum number increases and thereby lowering the ionization energy. But for mercury, the ionization energy is much higher since the electron has to be removed from relativistically contracted 6s orbital. So this was the trends in overall electronic enthalpy. So hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.